All right, so we started the last talk for this seminar series. We all totally may have up to 10 series, but this is the fifth of this series at this moment. And today we are likely to invite Mr. Wei Siwei. He was graduate from NCU, and he was graduate for his master degree. Then he started his PhD degree at SUNY Albany State University of New York. That's in the eastern side of United States. Currently, I'm not sure you are in Colorado or in
Colorado right now. Yeah.
In Colorado or New York?
Colorado.
Oh, in Colorado. Yeah,
we moved here.
His advisor has some mission, so he physically in Colorado. That's what his current location, and he will share with some of his experience on the use of GSI and present of aerosol in the model and how it works. I think that's useful for if you are doing some air pollution or air quality study, how to incorporate with the data coming from observation and how it represents in the model and toward to the next stage, such like data simulation. And through a good data simulation technique, then we can accelerate air quality forecast in the future. So everything will kind of step by step stacking toward to the successful air quality forecast. All right, so Mr. Wei sent us a pre-recorded video, and we also online. We will play the video at this next following, I think, 30 minutes, and then question and answer afterward. All right. Do you want to say something before you talk?
Okay, sure. Just a little thing. Since most people know the aerosol are related to the air quality, but in this talk, actually, let's focus on the meteorological analysis. So it's not really directly relevant to the air quality forecast. So that's the one point I would like to mention before the video start. Yeah. Okay.
Okay, so I talk about the future mission, and currently at this moment, the data analysis. Okay, yes. All right, let's start for the seminar talk.
Good morning, everyone. My name is Shiwei. Today I'm going to share my ongoing research work about aerosol data assimilation system. In this talk, I will focus on the response of CRTM simulation and the GSI analysis to the presence of aerosols. Here's my outlines. First, I will cover my background information and the knowledge about my research work, and then I will share my hypothesis and the two experiments to test it. And lastly, I will cover my future work and the conclusions. So what are aerosols? Aerosols are the small particles about around 0.1 micrometer to 10 micrometer aloft in the atmosphere. So the aerosol effects are well recognized in the climate and the numerical weather prediction research. So as the figures shown here come from the IPCC, they are fit. It shows the complicated pathway of the forcing and feedback of aerosols, greenhouse gases, and cloud in the Earth system. So we just focus on aerosols, those green arrows here. The aerosols can directly interact with radiation, which then adjusts the radiation budget in the system. Also, aerosol can serve as the cloud nuclei to affect the cloud formation and the lifetime in the Earth system, and adjust the radiation budget as well. In last couple of decades, most of our efforts focus on the physical representation of aerosol processes, like the ray effect, the interaction with the radiation, also the indirect effect, the interaction with the cloud microphysics part with the cloud and precipitation. So many studies already pointed out when we consider the physical description of the aerosol processes, uh, we can have a better forecast skills. In the modern NFP system, the DS system is another important component inside in the NWP system. So the DS system generate the analysis as a initial condition for forecast model based on the forecast and the observation information. Normally, there are three major sources, major types of observations are simulated in modern DS system. The first one is in situ measurement, and then retrieval and the satellite radiance observations. So for the in situ measurement, if the aerosol information, if the aerosol are affected, if the aerosols affect the in situ measurement, it will when the in situ measurement are simulated inside the DSs, and those aerosol information will be automatically propagated into the analysis. And for the retrieval data, many studies already come out some kind of atmospheric correlations to constrain those aerosol impacts on the retrieval quality. But for the radiance observations, most of the current DS system utilize the radiative transfer model as an observation operator to simulate those Brand's temperature measurement at the satellite. So, but most of DS system we don't consider the aerosol impact on the brain's temperature. But however, there are many studies already pointed out when we consider aerosols inside the radiative transfer model, you could reduce the brain's temperature simulation up to 60 degrees or even more when we have a heavier loading aerosols in the column. So like Socratic 2002 shows here, the x-axis are different IR window channel from different sensors, and she injects two kind of loading of dust aerosols into the radiative transfer model. Then, as you can see here, the Brand's temperature could drop to around about 60 degrees over the window channel. And also, this kind of cooling effect are also observed from the fuel campaign, which is documented inside the Highway Law 2003. Over the IR window channel, you can see 2 to 4 degree cooling effects over in their measurements. Given this kind of cooling effect given this kind of cooling effect on the radiance observations, we do actually can reject those aerosol affected observations, like ECNWF's approach. In Gill et al. 2019, he shows the aerosol contamination, the rejection rate of for the aerosol affected observations. As this figure shows, there are more than about 60% Yasi observations that are rejected due to the aerosol contamination in their system, especially over the Sahara Desert and the Middle East region. But we actually can have another option instead of rejecting those data. Like Weaver et al. 2003 and King et al. 2018, they provide the aerosol information from the GOCAM model into their radiance simulation, and then assimilate those aerosol affected observation burns temperatures into the system. And as a result, they show the warmer analyzed surface temperature and the low level atmospheric temperatures in their analysis. So based on those information I got from the previous studies, I'm considering if we can provide a better constraint and a better manipulation of those aerosol affected IR observations, we can further explore more information content from those observations and then improve the analysis and the focus. So to address this hypothesis, the first thing is how to understand how the aerosols affect those radiance simulations from the inside the radiative transfer model. So here in the next section, I will show the CRTM sensitivity test. In this section, I manually generate the dust aerosol profile to assess the sensitivity of the CRTM simulations. Those are dust aerosol profile I perturbed with the different aerosol loading and the different vertical distribution and the thickness and the different bins partition of the dust aerosol profile. As you can see here, here are two examples from the column mass density sensitivity and the peak altitude sensitivity. So in column mass density sensitivity test, I generate four different loadings of dust aerosols, and with the same peak levels of the aerosol profile. And then in the peak altitude sensitivity test, I used the same aerosol loading, but I changed the vertical distribution of the aerosol profile. And those sensitivity tests will examine those burn temperature simulation and the Jacobians. Again, I will examine those responses of burn temperature and the Jacobians in the CRTM. So here is the result of the sensitivity test of the burn temperature to the aerosol loading. So this figure shows the burn temperature differences between the simulation with the aerosols and the clear sky as a function of the wave number during the window channel of Yasi. So as you can see, when we consider more aerosols, which is green line, the largest loading I provided inside the CRTM simulation, we will have a stronger cooling effect, which is up to 20 to 25 degrees over the window channels. And if we if we fix the aerosol loading and change the vertical distribution of the aerosol layer, then we can see when the aerosol plume peaks at a higher altitude, higher level, then you will generate stronger cooling effects over the window channels. And another big component, important information provided by CRTM is the Jacobian. And here I show the one single channel result about the water vapor Jacobian over the y-axis, and then the temperature Jacobian at the x-axis for three different aerosol loading from the clear sky shown in the circle dots, and then the LD of 0.9 with the triangle dots over here, and the largest loading of LD of 2.7 with the square dots. And you can see when we consider more aerosols inside the system in the CRTM simulation, the the temperature Jacobian will become more positive, and then the water vapor Jacobian will become less negative. So, given that kind of cooling effects and the changes in the Jacobians, we can expect that the analysis increment will be changed as well in the GSI analysis. So in the next section, I will demonstrate the aerosol impacts on the GDS analysis with two experiments. The first experiment is the control run, which is the operational like experiment. The analysis was generated by the GSI analysis system with 40 EM-var strategy with 80 members. And in the control run system, in the control run experiment, the first case information will paste into the CRTM, and the CRTM will generate the balance temperature simulation and combine with the measurements. Then we can get the first case departure. And then after the bias correction and the quality control procedures, the assimilated data set will be determined. Then after the minimization process, the analysis will be generated as the next cycle's initial condition for the GFS. So there's another experiment called AER experiment that generate the branch temperature simulation with the aerosols information. It's a major differences between control run and the aerosol run. So in the aerosol run, we actually can consider that experiment is a aerosol aware experiment. And since I'm trying to focus on the simplify and purely demonstrate the aerosol effect on the analysis, so I didn't make the area run have the cycling structure as a control run, and we also use the same first cases from control run as the first cases in the area run. In this way, the aerosol impact on the analysis can be purely demonstrated through the comparison between the control and the area. So first, the first thing will be changed inside the after we consider aerosols in CRTM is the brightness temperature simulation. So here I provided the brightness temperature differences as a function of the wave number for those observations dominated by the different aerosol species. So as you can see here, the dust aerosols provide the strongest cooling effect over the infrared window channel, which is around the 4-degree cooling. Compared to the dust seesaw and the carbonaceous and the sulfate aerosols, didn't generate such strong cooling effects like dust aerosols. So based on the cooling effect, the first case departures will be changed as well. Then here I provide the statistics, the monthly averages, the mean monthly averages, first case departures, and the Loomis square first case departure as a function of the wave number from the AR run in blue line and the control run in red line. So here is the example from the YASI MeetHub A sensor. So you can see that in AR run, it shows a small, less negative features over the IR window channel, which is due to the cooler brightness temperature simulation. And then as a result, the Loomis square first case departure is slightly improved over the IR window channel. And after the first case departure are affected by the aerosols, then the best estimates are also affected. Here I show the different, the comparison of the total biases estimate from the control run and the AR run. As you can see here, in AR run we do have a smaller biases estimate after we consider aerosols, and it also has less lengthy differences compared to control run. As you can see here, the control run have a larger biases over the length, but after we consider aerosol, that kind of feature is disappear. And following the considerable change of the bias correction, then the QC procedure also be changed as well, since the GSI use the QC procedure in GSI use the bias corrected observation first case departures to determine which observations are assimilated, which observations are rejected. So here I provide the change of the quality control results in aerosol run with respect to control run. So the database is the table is based on the control run's QC results, and I will show the change of the aerosol run. So first row is the QC results. Those observations number. The QC result of the observations are identical to the control run, and the second row here shows those observations have a different QC results as control run, which means, so as an example, use the first column as an example. In this column, it shows the assimilated observation number. So this column means there are around 40% observations originally assimilated inside control experiment are rejected in the aerosol experiment. And totally, there are around 20% observation have a different results of quality control compared to the control run. So average overall, for most IR sensors, AER does assimilate more observations than control run, except on the AVHR and the Cerberus sensors. And for the assimilated data sets, there's a common way to assess the performance of the bias correlations. The PDF distribution, shows can be used to assess how the bias correlation works inside the system. So, as I show here, the histograms colored by the blue and the red are the result before the first case departures of before the bias corrections in the control run and the aerosol run. As you can see here, we have slightly more positive first case departures in the AER run. And after the bias correction, which shows in the dashed line, and we can see that aerosol run does have more positive skewness in the AER. The aerosol run does have a more positive skewness. This feature indicates that aerosol run, the assimilated data set is not really unbiased in the aerosol in the AER experiment. So given that kind of change, the more positive first case departures and the considerable change of quality control results, as a result, that analysis also be changed. Here I show the sea surface temperature differences between the AER and the control and the 850 millibar temperatures. As you can see, we do have a similar response as the results showed in King et al. And Weaver et al.'s studies. And we do have a warmer sea surface temperature in the lower atmosphere temperatures. And over the transatlantic regions, we have a similar structure that have a cooler mid-level and a warmer lower level. With this kind of with this kind of changes in the atmosphere temperature, we can expect that in AER run we do have a stronger instability, which would further affect the activity of the Africa easterly wave over the transatlantic regions. And I also validate the sea surface temperature analysis against the analysis with the sea surface temperature measurements over the West Atlantic, East Atlantic, Arabian Sea, and the West Pacific regions. So here is a table from the linear regression statistics of the analysis departures. So basically, there are not very significant improvement after we consider aerosols inside in the system. But we do reduce the co-biases of the sea surface temperature.
Questions? Yeah, for those people online, you also can ask as well. Okay, it's all completely open.
我想请教一下，就是分析 Jacobian 的意义，可以再多解释一下吗？谢谢。
好 ，Jacobian 其实基本上它是一阶微分，就是 Brownian temperature， 它的Brownian temperature simulation over the 就是它是一阶微分方程 for the Brownian temperature to the model state， 所以说它是用在那个 DA 里面，在这个方程式里面，在这个 equation 里面呢，这个 H 这个部分是 Jacobian， 所以它的目的在于它会因为我们的 radiance observation 其实是跟我们 model 的 focus variable 是不一样的 ，control variable 是不一样，所以就是我们在 model physics 里面是 temperature 跟然后我们的 radiance data 是 Brownian temperature， 所以我们是用 Jacobian 去做一个 conversion between 就是 mapping 那个model state 跟 observation space， 所以说从这个方程式来讲的话，H 就是 Jacobian，B 是 background error，R 是 observation error， 然后 delta Y 跟 delta Y 是观测跟模式之间的差距，然后 delta XA 是代表我们最后要修正的量，在模式预报上的修正量，然后基本上 H 呢就是把Jacobian 会 weighting 这个会改变这个 background error 在这个方程式里面的权重，那它就会进而影响我们到底要放多少的analysis increment 在model 里面，所以这是为什么我想要去看 Jacobian 的原因。
那可以解释一下第14页？
第14页吗？
增加气胶的量对于 Jacobian 的变化。
这件事情其实，是比较难理解的，就是说起来，我也没有到非常了解说到底为什么会有这样子的变化，因为它其实是一个透过adjoint function 去计算出来的变化量。那我能够给出来的解释，主要的解释比较能够容易理解的解释，就是 for 这些 temperature Jacobian 的部分，因为当我们把 aerosol 加进那个 radiative transfer model 之后，它会 block 住从底下上来的，从 surface 上来的 surface emit 出来的infrared radiation， 所以说藉由这样的经过它 block 就是它吸收跟散射之后，其实从 satellite 的角度来讲，它其实它会变成不是那么直接的去它会变得比较它会变得比较对于那个地表温度没有那么敏感，反而是对于 aerosol layer 比较敏感，所以它在有 aerosol 的地方，就是我这个color bar 的 color shading 的颜色代表的不同 level 嘛，然后就是我放了 aerosol， 其实基本上就是在后面这一段区域，那它就会变成这个意思就表示说 satellite 的 measurement 会变得比较sensitive， 对于那个 low level 的，就是 aerosol layer 的 temperature 比较 sensitive， 这样，这是我给他的一个解释。
那我还可以再问一个问题，我再问一个问题，就是这在你的演讲里面，大部分都提到就是有关于 infrared 部分。那不知道你们有没有对于 CRTM 模拟可见光的一些经验分享？谢谢。
CRTM 模拟可见光的波段的部分， 我之前在做的另外一部分研究是在AOD 的，就是 aerosol optical depth 的 data assimilation。那它跟这个演讲的部分其实会算是不同的方向，就是我们做 AOD data assimilation 的时候是去修正 aerosol 的 mixing ratio， 我们要去做希望能够得到比较好的 aerosol field。然后，可是我今天的演讲的这一块部分是在 meteorological 的部分。那对于 aerosol optical depth 的话，其实基本上，它现在也是有一些，现在也有一些其他人也在做这个部分的工作。那他们发现了一件事情，跟我之前看到的是类似的，就是还有大家都知道，大家都在说 CRTM 目前的 aerosol optical depth optical properties 没有到不是到非常的准确，就是它还是有一些误差存在，有可能是因为我们提供的 aerosol optical properties 不是最好，不是最准确的，不是 updated， 不是最新的版本，就是 CRTM 现在还是在继续更新它的 aerosol optical properties， 所以它还是有一些误差存在。对，那 visible 这是我目前我知道在 visible 可见光波段的部分说是对。
谢谢。
对。
就给一点 update 那个14页好了，好不好？就是那个14页 Jacobian the sensitivity of water vapor and aerosol on your page 14。请思维 share 出画面好，刚好 share 出来一下下。
有，我再来一次。
OK， 好。Okay, from Suez study, you will see actually the presence of aerosol has not only a response in window temperature, window channel brightness temperature, but also water vapor because it's a whole spectrum. So when Siwei doing the sensitivity study, he kind of doing the sensitivity for different aerosol loading, and also perturb the aerosol peak height. So that's showing in color bar. So at this moment, we would like to, I think the purpose for this study will become is nonlinear. Siwei using adjoint model. We also have the other way so-called tangent linear. But tangent linear also consider about one variable. So we can use the tangent linear method. When we consider two variables at the same time, adjoint model will become an ideal, very good choice on this one. But we need to separate the sensitivity due to either one, aerosol or water vapor. So we're doing this Jacobian study for water vapor and aerosol. This way, by using this way, we can know when during what kind of threshold or during what kind of scenario, which variable dominates than the other, or have more important impact than the other variable. Otherwise, without this one, we have no idea which one will important. Sometimes the effect will mix together, because you will see when the aerosol peak is low, in the low altitude, such like close to 900 hectopascal, you will see actually the sensitivity quite small in different loading, because the water vapor typically is concentrated in the boundary layer, so the sensitivity is not that huge. But when we see the aerosol loading when the aerosol peak is relatively higher, you will see the separation between these one. So by analyzing the Jacobian between two variables, it will help us to distinguish when will be the possible way to separate the signal by mixing two variables at the same time. 就是大概是用这样的方式去看，就是说，两个变数混在一起的时候，哪一个变数是比较重要，或者是在什么样的情况下，这两个性质是可以分开来看的。所以做这个Jacobian这个 study。 这样子。那如果只看一个部分的话，就会跟刚刚世伟做的前面的那两个部分一样，either 是 concentration 的不一样啊，整个 profile， 或者是这个就是那个 concentration 的 peak 在不一样，那个就是 one variable 的部分，所以单一 variable 做这件事情。所以这个就是为了要理清跟水汽的关系是怎么看。
谢谢老师您的补充，我还没有想那么多呢。
对，应该是我开始 JCSDA 那边吧，是不是他 suggest 你做这件事情，还是 BBC 比较像公司啊
？Joint Center 就是的确 CRTM 的 Develop Group， 他们 suggest 建议我去做画这样的图，然后但是我其实一开始只是想确定知道说，基本上我就在看说 aerosol loading 到底对于这两个变数它的同时之间会有同时看这两个变数的变化，对 aerosol loading 对这个东西这两个变数的影响这样子。
这个就是这个就是它 purpose 为什么要看这个模，因为那个你前面的那个即使是同样的高度，可是是不同的 loading， 可是它会造成的 response 不光只是 window channel， 就是大概 wave number 990那里到1000那里是window channel， 但是 water vapor channel 那里就是750到吧，你会看到它的 response 其实将近一半，就是 half of the window channel， 那个还是一个很强的 response 在这部分。所以当 aerosol 的 loading 在边界层有 perturb 之后，可是 water vapor 也是一个 variable 在这部分的时候，它就必须要厘清，就是说它的 sensitivity 到底是，就是 when you doing the O minus F 的时候 ，O minus B 的时候，is due to aerosol or due to water vapor， 因为你的 uncertainty 会来自于这两个部分，所以需要做这个角扣点的分析，是这样来的。
谢谢老师的补充，这我之后也会再多深入了解一下。
对，因为你in this simulation you already know， actually you fix the water vapor profile， 就是你是 fix water vapor profile， 所以这个算是就是已经确定了。So you only perturb 那个 aerosol 的 concentration， so it's very obvious the difference is coming from aerosol. But when we have variability in water vapor and aerosol, that's mixed effect. 所以就是透过 through your analysis of Jacobian between two variables, more straightforward to understand sensitivity, such like very low, such like a very low altitude in aerosol actually is different. It's very difficult to separate the signal from water vapor. 但是它的高度如果大概到750、600百帕的那个 in that altitude 600, 700, that will big separation between two. So that will become a so-called sweet altitude to separate aerosol impact from water vapor. 这样子。
了解。
OK，
谢谢老师的补充。
一起交流了，我觉得一起交流对。好像有个 question from online。OK， 文字的部分 ，OK，there is question raising from the text.
His question is that I have a question about the cooling effect by aerosol. Does the cooling effect in model sensitivity experiment include in the ray and the semi-Dirac effect, or just discuss the Dirac effect? Okay, for this one, for the CRTM sensitivity test, it doesn't involve any model integration, so it's only measure the snapshot, the instantaneous, just one. So it's basically the Dirac effect. So that's the absorption and the scattering from aerosol, and so even the semi-Dirac effect is not considered inside the sensitivity test.
Okay, I do have one. First, thanks you shared the response due to different species of the so-called particle matters, including aerosol and sea salt and the other thing. And the highest impact is due to aerosol as from your simulation. Just similar to the rest of the question. Because this is in window channel, aerosol, when we present aerosol in the model, the first thing will become so-called direct effect. It reduced the downwelling from short wave, in particular for the daytime, in the daytime. And then infrared will become secondary. Yeah, semi-direct, also called secondary effect. So is that possible the way aerosol has more significant impact than seesaw and rest of things? Because when I'm thinking aerosol is small particle than sea salt, and sea salt contains with relatively large giant particles in size. So scattering effect may not affect, but they have the direct absorption due for the short wave. Long wave aerosol less absorption than sea salt. So that's kind of imbalance between these two. So wondering, is that the reason caused? I think slide 24. Slide 24. Slide 24. You show a global distribution for the IR. Largest impact, especially warm impact in the Atlantic for the dust. But West Pacific, such like Philippines, is cooling. I'm not sure is that the reason. One is majorly due to dust, and the other region is due to kind of sea salt.
The thing I would like to for this question, actually, for the different response for Atlantic region and the West Pacific region, I think the dominant factor is the original forecast, the sea surface temperature forecast in the model. So basically, if I show from this table, you can see in the control run over the West Pacific region, the original analysis is the O-A is the negative value, which means the analysis temperature is higher than the offset measurement. But other three regions, they are opposite. So which means other regions have a cold bias, but the West Pacific region have a warm bias. So when we have a lower brightness temperature, after we consider aerosol inside the system, then we will provide a like for the warm bias region, which means the original analysis temperature forecast model is warmer than the observation. So when we have the lower brightness temperature, then the first gas departure will become larger. So over warm bias region. Okay, let me go over again. For the for the Atlantic region, the O-A shows for those region we have a cold bias, but for West Pacific region that's warm bias. So when we have a cooler brightness temperature in the first case, the forecast model, which means the first gas departure generated over the warm bias region, like West Pacific, is become smaller. So in this case, over West Pacific region, the first gas departure becomes smaller, then you will generate a smaller analysis increment. That's now, in this case, you will have a cooler analysis temperature than the control run. That's a major reason. It's not really related to the, I have to say it's not really related to any specific aerosol, but but you can see that we already know the Atlantic region are dominated by the dust aerosol, so that's why we will expect that's due to a different kind of aerosol. But actually, the major reason is due to the original focus area instead of the aerosol species.
Yes, I see. Yeah, because your simulation, your test is only considered about aerosol, not see. In this experiment, it's only aerosol, not include such like sea salt and everything. Yeah, I got it.
Yeah,
about you only control one variable coming from aerosols.
Yeah, I do consider a different kind of species into the ingested into the GSI system. So including the dust aerosol, sea salt, carbonaceous, and the sulfur aerosols. Those aerosol species are originally come from the GOCA model. Then using those information to affect the CRTM simulation. Yeah.
Okay. How? Any? Yeah. Yeah. Yes, microphone is here. You may come up. Can you hear me?
Yeah.
Thank you for your presentation. I see in page 18 about the dust, sea salts, and then I want to ask how to distinguish the component of aerosol like dust, sea salts in your analysis.
Okay, so you are asking about how to distinguish those aerosol species, right? Or do I understand right?
Yes. How do you distinguish the aerosol component?
Okay, for this experiment, I actually using the model output. So I actually didn't touch anything about the aerosols detection. So original model already give me what kind of aerosol species there, but for the next step in my future work, I would like to apply the aerosol detection method. That will basically majorly identify those observations affected by dust. Is more sensitive to dust aerosol. But for other kind of dominant species, we actually most of people they use the brightness temperature difference between the channel. Using that kind of a signature over the spatial signature, you can identify these observations are affected by the sea salt or the cloud or dust aerosol. That's the way you can somehow get idea about the observation affected by which kind of aerosols. Yeah.
Okay.
But in this study, yeah, we didn't do that. Yeah.
Don't worry. I see we have a participant coming from National Taiwan University, Dr. Zhang, Guoen Zhang. He is the one to distinguish the aerosol species. He has a work published, I think, 2 years ago. I think he is online. We also can invite him to share his work, in particular with his PhD thesis next time. 那国恩在线上啊，我看到你上线了，国恩啊，人家在问那个 partitioning， 就是那个 aerosol 的 partitioning， 那你的博士工作，不要再摸头发了，那张国恩准备一下啊，下次邀请你啊。Yeah, as Ziwei said, yeah, they are using brightness temperature. Actually, they're using reflectance differences between channels and also the slope between different channels to partitioning the aerosol type.
But that's majorly for the visible length, right? Visible wavelength, right?
Yeah, that's invisible waves.
Yeah,
because
so,
larger particle, smaller scattering, and smaller particle, higher scattering in wavelengths. So if you're using such like 0.4 microns and 0.6 microns, then they have different response for different species of aerosol type, such as sea salt or black carbon. So they're taking the consideration about that invisible band, they can distinguish the type of aerosol. That's the principle to detection and how to decide the weight, missing weight. Such like 100% of aerosol is coming from sea salt or black carbon, etc.
Yeah.
Okay, I think we take the last question from text. There's one from text.
Okay, yeah. This figure actually, that's the biases estimate in the first case departures. So it basically based on the different, it uses a weight to, like a linear regression method to estimate the first case departure, because actually first case departure already become, you can already consider that's a bias, but within that biases, it may involve with the sensor dependent biases or the radiative transfer model biases. So it's not really, I don't really have a good answer about for Eastern Africa region, there's some kind of small, higher or larger biases over this kind of region. But basically, I can say is inside the GSI, since the surface type is large, very uncertain in our forecast model or any numerical model. So for the CRTM, we actually for the bias correction, this part, we actually apply one predictor as with the surface emissivity sensitivity, which is the Jacobian Brand's temperature Jacobian for the surfaces surface emissivity. So it uses GSI use this predictor to try to estimate how many biases are attributed to the uncertainty inside the surface emissivity over land region. So with the higher biases over the Eastern Africa or in any area, which means that it probably largely have a larger uncertainty over that region. That's from the GSI side. That's the answer I can give you. Yeah.
All right. So that's I think we already have a 1 hour. 1 hour presentation. If no, then we appreciate Siwei's sharing about his most recent research work, and wish you the best during the pandemic. Thanks for sharing.
Thank you.
谢谢。
谢谢老师，谢谢你的邀请，谢谢。